Hey guys, today we're going to solve polynomial equations by factoring. Just like you saw in a previous lecture, I put the standards here just so you know what it is that we will be doing. Today we're not going to focus too much on doing a rough graph. We will be doing that in class on Monday. But for the most part, we're going to be utilizing zeros. We are going to find what types of polynomials could exist given the zeros, that kind of thing. So welcome to today's lesson. The essential question is, how does factoring help in finding the solutions to a polynomial equation? So we will discuss that today. Recall first off that zeros and factors are very closely related. So we've kind of talked about it when it comes to quadratics. If you recall that the zeros of a polynomial function are the x-intercepts. And so really that's what this little section is saying. If we have a polynomial function f of x, whether it's quadratic or cubic or quartic or even linear, it has a linear factor that is in this form x minus a if and only if the letter a, or the number a, whatever a happens to be, results in 0 when it's plugged into the function. So that's the main concept behind this, and this is called the factor theorem. So if we take a look at this, this will be something that you will want to add to your notes. The factor theorem states that if x minus a is a factor of f of x, then it's a solution to the function itself. So we are going to use this today, specifically in this example, so we can get started with this example so the video is not too long for you. So looking at this, it says to show that x minus 3 is a factor of this cubic expression. In this case, it's just an expression, not a function, but we will get to functions later on in the presentation. So we're trying to show that it is a factor. Well, if I'm using the factor theorem, I know that I'm specifically looking for whatever value I have for a, and I want to be able to plug that into my function and get 0 as a result. If I get 0, then that means that this is a factor. If I don't get 0, that means that it is not a factor. So pretty easy to identify both of those. So I'm going to start by writing this in function notation. So we've got x cubed minus 4x. Oh man. And this should be squared now that I'm looking at it. Plus 2x plus 3. So all that I'm doing again is evaluating at f of 3 in this case, just to see if it does give me 0 as a result. So I've got 3 cubed minus 4 times 3 squared plus 2 times 3 plus 3. So I'll write the square up here in case you guys need it. So looking at this, I know that 3 times 3 times 3, so 3 cubed, is really 27, minus 4 times 3 squared, which is 9, plus 6 plus 3. So really I have 27 minus 36 plus 6 plus 3. If I add all of these together, I do in fact get 0. So now that I've determined that f of 3 does equal 0, I can say yes, x minus 3 is a factor of that polynomial. For now, this is just an example of how to determine if it is a factor. So you would be given something and asked whether or not it is already a factor of that polynomial. We will get to factoring later on in the presentation. Another thing that I wanted you all to notice is this little bubble here. So this is kind of a refresher as to what zeros are and roots and that kind of thing. So if we have f of x and it's a polynomial, if r is a real number that satisfies any of these statements, so any of them, that means that it satisfies all of them. So if r is a 0 of the function, that means that it's an x-intercept of the graph, which we've talked about before. So remember that zeros and x-intercepts, those are closely related. Those are also referred to as solutions or roots. So all of these things are very, very important. And if you don't have them committed to memory, you need to know that these 4 things all mean the same thing. Again, the theorem that we just talked about a minute ago tells us, the factor theorem tells us that x minus r is a factor of the polynomial when r satisfies or when r is a 0. So this is basically the new thing that we're learning in the factor theorem. Going on to the next example, I'm going to write out a polynomial knowing that I have certain roots. So a polynomial with specific zeros, I want to find 3 different polynomials, different degrees, which is the key here, that have 1, 2, 3, and -5 as zeros. So if you recall, we can use the factor theorem to help us with this. So by the factor theorem, I know that this polynomial, whatever polynomials I end up writing, I know that they're going to have x minus 1 as a root. I'm going to have x minus 2 as a root, x minus 3 as a root, and x minus a -5. And then how do I know that? Well, technically all of these numbers that are provided to me are the a that we were talking about in the factor theorem. So x minus a, which all of these happen to be the a's. Notice I wrote this one a little bit differently. So if I rewrite this, technically x plus 5 would be a possible factor. So there are infinitely many polynomials that I could write that contain these factors. I'll just name a couple just to kind of get us started. So I could say that I have a polynomial function g of x, and I could just write these as is. So I could say, well, I've got x minus 1 times x minus 2 times x minus 3 times x plus 5. That would suffice as a polynomial possibility. Note that this one would be a polynomial of the 4th degree, because if I multiply all of these out, I have 4 of my x's, so that would be a 4th degree polynomial. I could write another example, say that I wanted to write h of x. I could write almost the exact same thing, but put a coefficient in front of it. So say I have 8 times x minus 1, x minus 2, x minus 3, but I could say that I have x minus 3 squared. Say I've got 2 of them, that's all right, and x plus 5. So ultimately, as long as these 4 roots exist somewhere in my polynomial, that's really what I care about. Again, if we take a note of the degree of this polynomial, this term is being squared, so I have 2 degrees, 3, 4, 5, so h of x is a 5th degree polynomial now. So just to take note of that, I don't have to multiply it out to determine what degree it is. I can just take a look at the number of x's that I have. I could also write another example. Oh, just to go back, sorry. This term here, the x minus 3 squared, this is called a double root. So just a note to yourself, and we will see double roots when we start to graph. But just make a note to yourself that if there's a root that is squared or cubed or anything like that, if it's squared, it's a double root. If it's cubed, it's a cubed root. So that kind of thing, just make a note of that because we will see that again in the future. So if we're looking at this, another polynomial function that I could write, again, there are infinitely many, but in this case I wanted to find 3 of them. So my third one could be 2 times x plus 4 squared. Notice that this isn't one of the roots that was given to me, but I could introduce new roots. It doesn't say that those are the only roots. I could have my x minus 1 next to it, x minus 2, x minus 3, x plus 5. I could get crazy and then add x squared plus x plus 1. So ultimately, as long as it has those roots in it, we can use the factor theorem to help write a polynomial. I could multiply this out if I wanted to. If I wanted to determine the number or the degree of this polynomial, I've got 2 here, 3, 4, 5, 6, 7, 8. So this would be an 8th degree polynomial. K of x would be an 8th degree. So take note of that just so you guys don't feel like you have to multiply it all out to identify its degree. The next example, I think that was it for this one. So next example we're going to look at is to find the zeros of a given polynomial function. So now I'm not determining, or I'm not given any information about the zeros. In the previous 2 examples I was. In this one I'm actually trying to find them. So this is where it gets a little bit harder. Not too bad, but a little bit trickier and more complex. So if I'm looking at something like this, First, I've mentioned this before, we always, always, always want to figure out if we can factor something out of this, out of this function. So when I take a look at this, I can look at every single term and I see that there is not one thing that I can factor out of all of them. So from there, I can go ahead and I'm just going to rewrite this so that we can get it started, usually a recommended practice. So I've got this written out. What we're going to show today is how to factor by grouping, specifically in this example. So if I look at this, I know if I'm finding a 0, that means that my function should equal 0. And I'm actually just going to put a 0 there. So I know that f of x should equal 0. The function stays the same. If I want to group this, I specifically want the same sign between both terms. So if I were to put parentheses around this, I see that there's a plus sign in the middle. If I put parentheses around this, though, there's a minus sign. So I want to rewrite this in a way to where there's a plus sign in between both of them. So I'm going to keep this one grouped because that one looks fine. This one, though, if I factored out a negative, then that means I could have 6x plus 15. Distributing that would get me what I had before. Now I've got the plus sign in between both of them, so I can start to factor things out. Here, the only thing that we have in common is our x squared. So if I factor that out, I'm left with an x plus 5, 2x plus 5, I lied. So the next one, I want to see what I can factor out of there. These both have a 3 in common, no x's, so I'm going to leave my minus sign there, put the 3, and I'm left with 2x plus 5 again. Notice we've done something like this before, so our two parentheses are exactly the same, so I'm going to factor out those parentheses, so 2x plus 5. If I factor that term out of both of these terms, I'm left with x squared minus 3. But I'm not done yet. We're not just factoring, we're actually finding the zeros. So now I need to set both of these factors equal to 0. So I've got two scenarios. I've either got 2x plus 5 equals 0, or I have x squared minus 3 equals 0. So solving this one, subtracting 5 on both sides, I get a negative 5 over here. Dividing by 2 gives me negative 5 halves. And then over here, adding 3 to both sides gives me a x squared equals 3. Taking a square root of both sides, I have positive or negative root 3. So if I'm finding the zeros, I want us to get into the habit of putting them in coordinate notation or coordinate form. So this would end up giving me a point of negative 5 halves, comma 0, because we're talking about x-intercepts here. This is two solutions, remember, so I have a positive root 3, 0, or I have a negative root 3, 0. So these end up being all of my zeros, and it makes sense. If we look at our polynomial, I could have up to 3 roots because it's a third-degree polynomial, or it's a cubic polynomial. So in fact, I do have 3 roots. I will not always have 3 roots, but in this case I do. So up to 3 is the maximum. I could not have 4 in a cubic function. So looking at our next example, again, I'm going to start off by trying to determine if there's anything that I can factor out of this polynomial before, or any number that I can factor out of each term. In this case, it may not look like it, but I can actually factor out a negative 1/4. So again, if I'm solving, I know that I'm setting equal to 0. And if I factor out a negative 1/4, out of every single term, then I'm left with x to the 5th, and then a negative 3x cubed, and a negative 4x. So not something that's easily seen, but make sure that you are considering these different options, because this polynomial is now a lot easier to work with than something that has 2 fractions in it. So now that I've got this, I can see, oh, well, there's also an x that I can factor out. So I'm going to have a negative 1/4 x. Here I will have x to the 4th minus 3x squared minus 4. So once I've got it in this form, what I'm going to go ahead and do is factor by grouping again. It's not as easy to see here because I only have 3 terms, whereas before I had 4 terms. So I'm going to rewrite this in a way that it has 4 terms. You can use the chart that we had made before with quadratics where we have the A, C, and B column. So here A is 1 and C is negative 4. So really A times C is negative 4. B is negative 3. So this doesn't only work for quadratics, it works for polynomials in general. So I know that my factors could be 1 and negative 4. If I multiply those, I'll get negative 4, but if I add them together, I'll get negative 3. So I'm going to rewrite this as negative, and I'll just put x over 4 just so we know that these are both the same thing. I've got x to the 4th, and I'm going to specifically keep the x squared here with it, and the negative 4x squared. Notice that I got the 1 and the, sorry, this is a positive 1. So I got the 1 and the 4 from these factors that I just took. So these numbers are the ones that I used over here. And then I'm going to keep the negative 4 at the very end. The reason I grouped it this way is because I saw that I had 2 4's, so I know that I can factor a 4 out of both of these terms, and then I can factor out an x squared out of both of those. So again, negative x over 4. Looking at both of these two terms, I'm going to factor out, or we can rewrite it in a way where we have a plus sign in the middle again, just like one of the previous examples. So I have a plus sign here, I want a plus sign here. So these are the two that are already grouped. They're good to go. I'm going to factor out a negative sign, so now I've got 4x squared plus 4. Makes it a little bit easier to see. You don't have to do this if you're already comfortable with factoring. So once I move on, negative x over 4, I'm going to look at this and say that I can factor out an x squared. I'm going to use brackets here, so x squared. If I factor out an x squared from both of these, I'm left with x squared plus 1. Here I'm going to factor out a 4 like I stated earlier, so I'm left with x squared plus 1. Notice that I have 2 of the same term again. So 0 is equal to negative x over 4. And then now I'm factoring the x squared plus 1 term out, so x squared plus 1. If I factor that out of this term, I'm left with an x squared. If I factor it out of this, I'm left with a minus 4. This is the factored out polynomial, but I'm not done yet because I need to solve the polynomial. So, and actually I noticed that I have a difference of squares. So if you recall, if you're not comfortable with difference of squares, please see me during tutoring because I will explain it to you. But this is a perfect square, this is a perfect square. So I can actually factor this just one little bit more. This term stays the same, x squared plus 1. This one ends up being x plus 2 and x minus 2. So again, if you're not sure how I got from this step to this step, please see me in tutoring and I can go ahead and explain that to you. You can use the box method to factor that as well and it will work. But the important thing is recognizing that you have a difference of squares. So this is a perfect square, that's a perfect square. Okay, so going back to this, let's see. I now have to set all of these different terms equal to 0. So notice I have 1, 2, 3, 4 different terms that I'm going to set equal to 0 to actually find what my zeros are. So I'm going to do this in a different color just so it's not so brown and redundant. I could have negative x over 4 equals 0. If I multiply both sides by 4, I get negative x equals 0 still, so x really equals 0. So I know one of my roots is going to be 0, 0. If I look at this next one, I have x squared plus 1 equals 0. So if I subtract 1 on both sides, I have x squared equals negative 1, which, we've seen that this doesn't work unless we use imaginary numbers. So I know that this is going to be an imaginary root, and it's not actually going to cross the x-axis. So this is where we get into a scenario where I have a polynomial of degree 5, but I'm not necessarily going to have 5 real roots. So going back to this, I'm going to leave this one alone. The next one would be x plus 2 equals 0, which means that x equals -2. That's another root, so I've got -2, 0. And then my last one, x minus 2 equals 0, which means that x will equal 2, so 2, 0 will be my last root. So in this case, I only have 3 real roots, and then I have an imaginary one, which we're not going to spend too much time focusing on imaginary, but we know what they are now that we've studied quadratics and imaginary numbers. So this polynomial, this 5th degree polynomial, is going to intersect my x-axis only 3 times. So please let me know if you guys have any questions about this in class tomorrow. The next and last slide for us today is identifying a sum and difference of cubes. So we've talked about a difference of squares. There's really no such thing as a sum of squares because that's when you get into imaginary numbers, but there is a sum and a difference of cubes. So add these two to your notes. They look very similar in format, however, the difference is in the signs. So the setup, the structure is the same, but the signs are different. So if you have something cubed plus something cubed, you factor it in this way. And what this is telling us is if I have a plus sign, I'm going to use a plus sign first. So I have whatever a and b are first with a plus sign in between. I always remember that the first and the last one are going to be the same sign in this case. And then the only thing that's different is this second sign in here. So plus minus plus. If we go to a difference of cubes, I have same sign again first, so that will always be consistent. Opposite sign will be next. The last one is always, always, always a plus sign. So try your best to remember this. I know Miss Romero has a way to memorize it, so you can ask her if you'd like to. I've never thought of any type of acronym to memorize this, but we can do that in class. So if you guys do want to think of some way to memorize it and we find that it's catchy, then I wouldn't I would consider giving you guys extra credit if you can think of a jingle or a way to memorize the difference of cubes, because that would help everybody. So ultimately, I'm going to use the difference of cubes to solve the next polynomial function that we have. So if you needed to go back and pause the video, you can do that to take a note of those these algorithms to write down. So example 5, solve the polynomial function g of x, and it's -27x cubed plus 125. So looking at this, we actually have 2 perfect cubes, which is why I picked it. So 27, I know that 27 is 3 cubed. 3 times 3 is 9, times 3 is 27. So what I'm going to do is, since we're solving, again, I'm going to set this whole thing equal to 0. I'm going to rewrite this as something cubed plus something cubed. And this will help when I start to use these algorithms that we had written down up here. So 27, notice that it's -27, so that means it's not a positive 3 that I'm using, it's actually a -3. So I've got -3 and then the x. If I cubed both of those, I would end up with this first term here. The next thing would be 125, and so 5 times 5 is 25, times another 5 is 125. So my b in this case is 5. So knowing, excuse me, that a is equal to -3x and b is equal to 5, I can now use the algorithm that was written above. So we've got the 0 is equal to, and you recall that it was a plus b, so we're using the same exact sign, so same opposite plus rather. So -3x plus 5, so same sign as before. And then now this is where we get a little bit different. I've got and I'm going to use brackets here actually, so I've got a -3x squared plus a -3x, remember same sign as before, and then I need to multiply by b, which is 5, and then always plus sign at the very end, and then I've got b squared. So now it's a matter of multiplying these out so that I can finish solving it. I'm going to leave this the same. Just a side note, I think it's funny that the closed captioning actually puts the word gonna. I didn't know that it did that. So negative 3x squared, negative 3 squared is 9, and then I've got the x squared. This would give me a negative 15x. This would give me a positive 25. So this cannot be factored anymore typically. This one is completely factored out as a difference of cubes, so there's no way to simplify this anymore. So now I've got my two factors. I need to set both of these equal to 0 to actually solve the polynomial. So I've got 0 equals negative 3x plus 5. So if I added 3x to both sides, I would have 3x equals 5, or x equals 5/3. So there's one of my roots. It's 5/3 0. The next one, I'm going to do this, which we said that we can't factor it anymore. If I can't factor it anymore, then that would mean that it doesn't have any other real roots. So this one actually has no real roots. I can double check it if you're ever not sure that you did this correctly, and we can use the discriminant. So b squared minus 4ac. If I took the b, it'd be negative 15 squared minus 4 times 9 times 25. So negative 15 squared is 225. And then I have minus all of this stuff multiplied together, which gives me 900. So 225 minus 900 is negative 675. If you recall on our quadratic notes, we said that if we have a negative discriminant, that tells me that there are no real roots. So in this case, I only have one real root. Although I started with a cubic function, my cubic function is going to intersect my x-axis at one point, and that one point ends up being 5/3. So consider that you can, again, I've said this before, you can have up to 3 roots, but you will not always have 3 roots. So to give you an idea, if I had the graph of this, I know that my x-intercept is at 5/3, and it's a positive. So we know that this is an odd function, which means, and the leading coefficient is negative, which means that it starts up here, and then it goes down, goes back up, and then, hold on, sorry, I messed that up. No, I didn't mess that up, I lied. So starts at the top in positive infinity, crosses my x-axis, and then eventually it starts to go back down in the opposite direction. So we remember that odd functions go in different directions. So to give you an idea, that's kind of what this one is looking like, is it goes up a little bit, but not enough to cross again. So we have one x-intercept. So hopefully we have a better understanding of how to solve polynomials. We're still using a lot of the concepts that we used in factoring quadratics because a quadratic is a polynomial. So now we're just extending it to polynomials of higher degrees. So I know that there were no puns in this. Daniel, I apologize. However, I did find a kind of funny little comic that we can look at. What's his problem? Oh, don't mind him. He's just odd. So our poor little odd function. And it's almost like they're raising their hands like, huh? What is his problem? Anyway, I thought that was kind of cute. So I'll see you guys on Monday. Have your notes ready. We will have a notebook check on this set of notes, the set of notes that we took Wednesday and Thursday in class. If you are not in class, those notes are online on my website. And then also the video for systems of linear and quadratic functions. So 3 sets of notes that I'll be looking at. Make sure your table of contents is also up to date. And otherwise, we are good to go. So I will see you guys on Monday.